Okay, so today is March 24th, a very snowy March 24th, but you should have submitted your tutorial 8 this past weekend, and tutorial 9 and assignment 4 are due this weekend. And then tutorial 10 will come out. Tutorial 10 will be on the standard template library. So what I'm doing is actually I would normally do exceptions after templates, but we're going to jump into the STL. These two topics, it doesn't matter which order you do them in. We'll save exceptions for last. Um, what else? Yeah, standard template library is your tutorial 10. I will probably also that week open up the rest of the tutorials again. Okay, so if anybody's not happy with their mark, this is your chance to make back some marks. Um, I take the top, whatever it is, I think it's 8 out of 10. And that's for, I think, 8%. But usually what I do is if you do all 10, they'll just count for extra. Okay, so if you have an assignment that you didn't do so well on or whatever, this is your opportunity to make some of those marks back. All right. Other than that, I think we're coming to the end. So next week also, or at that date, at the latest, we'll talk about the final exam, although I'll mention some stuff about it as we go. I have a good idea of what's going to be on it, but I'm going to write it up officially tomorrow, so I'll have more information after then. But yeah, questions? Okay. So last class, we were talking about templates. And we had left off here. We basically finished templates. Right? So we talked about, you can have multiple template arguments, you can have different type arguments, and yeah, sorry, I hurt my ribs on the weekend, so I might be a little, it's just my breathing is a little labored, so I might be, I might take a breath now and then, and yeah, so templates really are parameters. You can pass in actual arguments, you can pass in types, right? Class is really just another type. So when I say class T, I mean, well, something that resolves to another type, right? But then I can also put an int or a time or whatever. All right. And then we can put in, because they are actual, sort of really parameters, you can just use default values for them as well. So those are the things we looked at. All right, some of the limitations in C++, right? Because it is really a primitive way of doing templates, right? This copy, paste, find, replace. So what are the limitations? Well, they don't really, at least not in these versions. I mean, I am not up to date on the latest and greatest in C++, but they don't do, as far as the version that we use, any sort of, right? If this was Java, I could say, what is it? T extends, and then I could put number or something like that. And then T must be a subclass of number, or child of number, or an ancestor of number. You can't really do that in C++, so there are like hacks, right? So what we can do is we can write some function like this that I'm going to say, well, I want to make sure that T is of type base class, right? Or a child of base class. And so, well, if I make a piece of code that takes a base class pointer and assigns it a new T, then that should compile. And if it doesn't compile, then T is not an ancestor of base class. The key here, so this is like a useless function. We're not going to use, but you have to call it to get it to compile, right? So if you don't call it, it's not going to compile, and you won't potentially find this error. So it's a little weird. I don't know. Maybe in the current version of C++, this is baked in somehow, but as of the version that I'm used to, this is how you would do it. All right, so that's templates. So we're going to, I mean, we have all the tools now to build like our own collection classes, right? Maybe not to the level of, we're not going to make dynamic arrays that grow and shrink and things like that, but like a linked list we could make. But of course, we actually don't we don't really want to make them. You can actually. I mean, there's nothing stopping you. And sometimes it might even be a good idea because, things like the standard template library, although they are, probably very good and almost certainly, want to say almost certainly bug-free, but, nothing is ever certain. But it'd be very rare to find a bug. But they are kind of heavyweight, right? There are a lot of functions and stuff that maybe you don't always need. They're meant to be very general. But they are a good option. If you're building something, you don't want to roll your own collection classes, then you're going to use a standard template library. And the standard template library is, as the title suggests, a bunch of templated classes. So we're going to start looking at some of them. Actually, right after this, we're going to look at we're going to dive into this in detail, but there was a little primer in this section. So we might as well just walk through it. Talking about the vector class. And so we've actually seen this example before. We have a vector, and we're going to make it a vector of student pointers, and we're going to pass in a bunch of student addresses, allocated students, and then we're going to print them out. Okay, so yeah, we mentioned when we make the students, and we mentioned when we destroy the students, and then here's where they're all printed out. Okay. This is, we're using a for loop here, and of course, being savvy C++ programmers, maybe we want to use the overloaded stream insertion operator, but it is not overloaded for the vector class, right? So we, in our previous examples, overloaded it for, let's say, was it a book array or something? And we saw at least one potential problem is that if you overload the stream insertion operator, you're making some assumptions about the type of data that's being stored. So in the case of the books, we ended up printing out the memory addresses instead of the information that we wanted. And this vector is storing student pointers, and we really don't want to print out student addresses, right? Like not memory addresses, that is. So what is the solution? Well, we can just simply overload this operator for a specific type, right? We don't have to make this a templated function. So I can overload the stream insertion operator. We might want to make it yeah, we'll put it here. This will be for a student. And let's make that a friend of our class. Did we make it a friend? We did. All right, perfect. Oh, wait, did I write it somewhere already? I don't think so. Okay. Oh, sorry, not for student. I want to do it for vector. That's the problem. Okay, so const, const vector. And then instead of a templated type, we're just going to put an actual type. We're going to say, well, we want to overload this for a student pointer, right? In this case, we're storing student pointers, students. And then, then it's a simple for loop after that for int I equals 0, I is less than students dot size. And then we're going to print them out, but they are student pointers, so we have to dereference them, right? So that's the advantage of, instead of writing a templated function that it's a catch-all, whatever I put in my vector, I will print it out. The vector, the people who made the standard template library decided, well, we're getting too specific now, right? I don't know what you want to do, if you want to overload this or not. And if you do overload it, then how do you want your data formatted? So they don't overload this stream insertion operator, right? So we are free to do it, of course. And I'll say students. And then I can the advantage of knowing the type is that I can dereference it here. So then I don't get the student addresses like before, and then this should work. Oh yes, well, of course, I always forget to return this. And so yeah, now we have a stream insertion operator that works, but of course we just have to write one for each particular type that we want. That might be the best idea. I could also make a templated version of this, but for this instance, I don't want to. All right, questions? Okay. All right. I swear, man, I miss being young, where I could just like do something athletic and not pay for it on Monday. But so some of this other stuff that we've seen this before. So the at function for our vector class, of course, this does bounds checking for us, right? So that's the real difference. If I say at 1 or at 3, these are valid locations because I have 4 students. If I say at 10, this is going to throw an exception. Now I can catch the exception and then handle it, or I can just let my program crash. But either way, at least I'm not accessing memory that's out of bounds for me. Right, so yeah, student at 1, student at 3, and then student at 10, I get this bad index error. But my program keeps running because I decided to handle it. One other thing to look at is, well, we've added 4 students, or wait, 5 students. Timmy, Jimmy, 4 students. Okay, well, let's start with size and capacity. So there's 2 functions here, size and capacity. And so when we run them, we get capacity is 4 and size is 4. Let's add one more student to this. I don't have another student, but let's make one. Pushback. Basket weaving, sure. I think I have some default values here, don't I? 10.0F. Oh yeah, sorry, geez. These aren't student objects. So let's make student Bob. Good old Bob. We'll push back the address of Bob. Okay, so with 4 students, my size and capacity are both 4. I'm going to add one more student, and size and capacity, we'll take a look at what they are. And then, so I went from having a capacity of 4 and a size of 4. I had 4 students, which is the size, and the capacity is basically the size of the backing array. And then I added one more student, Bob, and we can see here that the capacity doubled in size. So I have 5 students now, which I completely expect, but capacity gives me the size of the backing array, and that is doubled in size to 8. And if I had, put a print statement in the copy constructor, we would have seen that a bunch of copies were being made. So what happens with my vector, which I may have mentioned at some point, but if I have a backing array of size 4, and my vector is pointing to it, and then I try to add one more, well, it's going to double in size. It's gonna make sure that I have enough room for, the foreseeable future. And then it's gonna copy these 4 items over, and then it's gonna add Bob here at the 4th location or the 5th location, index 4. Okay, so right? Not that, so we didn't implement it that way, but this is useful to know because, well, of course, we're using pointers here. So I'm storing a vector of student pointers. So when I make these copies, I'm just copying the memory addresses, right? So that was a good design decision because I am going to be making a lot of copies of them and I don't want to copy the entire student object. But there might be other instances where we actually want to store a student object. And in that case, maybe vector is not the best idea. We'll go over that in more detail a little bit later. Vector also has a copy constructor. This is not a deep copy, right? I mean, because a vector is a template, so it doesn't know if it should make a deep copy or not. So if I want to make a deep copy, I kind of have to do that myself, right? I can write a little function that just iterates over one and makes a deep copy of it. But in this case, I'm just going to copy all of the memory addresses to the students that are sitting on the stack. And then I'm going to compare them, this double equals. And so are the vectors equal? The answer is yes. Okay, so when I do that copy constructor, yeah, I end up, and what does it mean to be equal? It means that, maybe we should come back to this later. We are literally jumping into the standard template library right after this, but just briefly, what's happening here is that, all right. I believe I cover this later also, but just in case. So we made this copy of COMP2404. It's COMP2406. We said 2404 is equal to 2406. We looked at the capacity of 2404 and 2406. Or when we looked at the capacity of 2404, we had a size of 5 and a capacity of 8. And so let's see what happens with our copy. Okay, so are the vectors equal? Yes, but my 2404 has a capacity of 8 and a size of 5, while, sorry, this should say 2406, while 2406 has a capacity of 5 and a size of 5. All right, so if we go back to our little diagram, my vector had a size of 8, and it had A, B, C, D, and Bob. So it had a size of 5 and a capacity of 8, and when I made a copy of it, well, I only needed 5 locations, 1, 2, 3, 4, 5, and then I copied all of these memory addresses over. Okay, so the copy constructor does not copy the size of the backing array. It just makes enough room for whatever's being stored and then copies it over. All right, questions? I think we're going to skip the rest of this because we're literally jumping into standard template library right after this. So, all right. Before we do that, I'm going to look at one more thing. Yeah. So yeah, a couple things to note, of course. If we have a vector of pointers and I make a copy, it is not a deep copy, right? I'm just copying the memory addresses. So the last thing we'll look at is just smart pointers. This is a short example. But we had made a smart pointer, which is a pointer that automatically deletes memory for me when it goes out of scope. We had done one for the time class, right? So it stores a time pointer, and then when it goes out of scope, well, my destructor will delete it for me. So I don't have to worry anymore about when this time variable gets destroyed. It's tied to the life of my smart pointer, and my smart pointer is statically allocated so that once I exit whatever function I allocated it in, it gets cleaned up for me automatically. Okay, so. Okay, so yes, I mean, terrible formatting, but I did print this time variable twice from this smart pointer. But now well, maybe I want to make a smart pointer that, for instance, works on ints instead of the time variable, just the time variable. So let's take a look. It won't take very long, but we are going to make a slightly different decision than we made typically before. I want this to be a templated class. Well, yeah, the implementation is already here, so that's good. Instead of time, well, before we went through, we changed all the book pointers to T, right? Because we didn't want to make assumptions. We wanted the user to be able to store either a pointer or an object or whatever they wanted. But in this case, I know that I want a pointer, right? This has to be a pointer. So I'm going to sort of make the decision that when the user declares this, they're going to use the type itself rather than declaring it as a pointer, right? I mean, just a small design decision, but it means that we're going to do things slightly differently than we did before. When I declare these things now, before it was just T, but now I'm going to say, well, it's actually a pointer to T. Okay, so we're going to enforce that at this application level. T reference. Well, if I dereference this, I should return. Yeah, that should be fine. I should return an instance of T. This is a T pointer as well, and yeah, that should about do it. So really, again, it's a short example, but the only thing we're doing here is we're also supplying this dereference operator, or this pointer operator, and we're sort of enforcing this the fact that it is a pointer. We're not leaving it up to the user to mess that up. Okay, so this seems to work. Let's see if we can print some time objects the same as we did before. And yeah, we have this terrible formatting. We can also make this int. And what can we do with an int? We can print it. Dereferenced, of course. Right? So this smart pointer acts as a pointer, so we dereference it to get back the number. So we should get back the number 42. And we do, and I did not delete anything, but everything should be deleted for me. And look at that. So our smart pointers are working. Okay, so that's it. Questions? Okay. Or is that a question? No. All right. So yeah, let's do a little woo clap. We'll come back to this after. So a short woo clap. I'm running out of inspiration. I don't know. It's the end of the semester, right? I don't know. Just making your exam. I'm tired of the snow. I'm ready for the sunshine, man. And yeah, like I said, when I run out of inspiration for the exam, I go looking at WooClap, eh? So it's good to pay attention to these questions. I might change them a little bit, or sometimes, give you exactly the same one. So we want to overload the stream insertion operator for a class template foo, right? So which of these would be the correct declaration? So I don't know what you guys can see, but technically this is enough information to make your decision, right? So we are declaring a function template for this stream insertion operator. We want it to be a friend of our class. And so how would we do this? And yeah, I guess, so let's start talking about why, what decision we might want to make and why. But when we declare this function, a friend, it's sort of it's a weak forward reference, right? It's not like a weak forward reference. It is a weak forward reference. And as a forward reference, if it's a templated function, then we have to declare it a template. So we absolutely need a template declaration, right? We have to, this is basically, I'm just forward referencing a function. The friend is sort of immaterial for this. The question is V or T? Well, these are in some sense variables, and like variables, they have a name, and those names can get into naming collisions, right? So if I declare a template T here, well, that is just for this, but I'm now hiding that class T, right? I'm shadowing that T parameter, which means I can't really use it anywhere else in my class. If I try and use it, it's referring to this, and probably I'm going to end up, or hopefully I'm going to end up with some weird errors. So yeah, it's number one. We have to declare that that function as a templated function, and also we have to use a different variable name when we do it. All right, questions? Okay. Yes, when using a class template, which of these file structures are recommended? So I want to put the declaration and implementation into separate files, or I want to put them both in the header file, or whatever that means. And, I guess why would be for bonus marks if I was asking something like this. All right, so yeah, we do want to put them both in the header file, and the why is that, well, if I separate them, then they're not an instance of a class until I have a type. And just if I have the header and the source and I try and compile the source independently, well, I don't have a type, so I can't compile it. So it's really pointless to do it that way. I have to, in some sense, include this code in some location where I've declared a type, and then it can be compiled. So that is the sort of the short answer. I'll let you guys, anybody who didn't vote can still get in there. Given the following template and code, how many classes are made? Right, so this is probably the last thing we covered last week. We're talking about we can put values as a parameter argument, but of course, what happens? So how many different classes am I making here? So if we go back to first principles and think, well, what does the compiler do? The compiler does a copy, paste, find, replace, and then tries to compile it. And so it's going to go here and say, well, copy, paste, find, replace, and compile it. And assuming that it's successful, now it has a class of foo with time and 5 as the parameter arguments for this template. And then it's going to go down here and say, well, I need another class with time and 5. Well, I already have a class. I technically can't even compile a second class if I wanted to, because it would look exactly like the first class. So we just reuse the first class. So these two are the same. So this is 1. Down here, we just changed the value from 5 to 4, but I mean, it might not compile now, right? That is possible. Kind of unlikely, but you could do something. You could branch on this value and have a piece of code that doesn't run, that didn't run in the previously, but now it runs and now it doesn't compile. So technically, this is a different class. This has to be a different class, so we have one here. And of course, when we change time to date, we also have to recompile it and make a new class. Okay, so these are three different instances of classes. And yeah, two-way. Yeah, so that I'm guessing here at what the people who guessed two, maybe they just guessed, I don't know. But that integer, just changing the integer means I need a new class. All right, questions? Okay. All right, I'll leave that up. I think that's all the questions. I'll leave that up in case anybody wants to get a vote in. That brings us to standard template library. So this is right. So templates is the last part of your assignment for standard template library. I'm doing it first because so that when we start next week, you have all the tools to do tutorial 10 if you so desire. So yeah. Oh. I got a little dot there. Okay, so standard template library. Well, what is it? I mean, it's the set of collections that, generally speaking, are used with C++. And what is in it? Well, iterators we're going to talk about, containers and algorithms. So containers we're familiar with. We've made a bunch, right? It's just something, a collection class, essentially. They're called containers in C++. Algorithms, well, you're probably a little bit familiar with, right? Maybe we want to sort one of our containers full of things, or maybe we want to, well, there's other algorithms, find the max. I mean, these are simple things that you could usually just make yourself, but they're also made there for you if you like. Iterators are a little new. These are a design pattern. Again, they're just another layer of abstraction. So I want my algorithms to run on different containers, but of course, you know, if I'm sorting an array-backed list, it's very different than if I'm sorting a linked list, right? The instructions are different. So what do? I want to like move this thing over here, and so that means if I want to sort, every sorting algorithm will have to be written for both a array-backed list or a linked list. And then so iterators provide this common interface of an array-backed list and a linked list, so that when I run my sort algorithm, I don't have to worry about what's behind the scenes, right? I just say, I have an iterator, I say like, get me the next thing. I want the next thing, and then move this thing over here, and the iterators figure out how to do all that, right? So it's an abstraction layer between the, getting a little ahead of myself, but. So yeah, it's a library of classes and algorithms that operate on those classes, provides useful container classes and member functions like vector. Iterators can be a little weird to work with. They look a little awkward. Also, we got to watch out for the copies, right? The standard template library will make many copies, which incidentally, that's one of the stories. There's a little news story about how Meta found an error just in C++, right? So they, of course, every company just about has a layer of C++. And they found an error, which was just, they passed by value instead of by reference. They were passing vectors by value instead of by reference. I mean, well, let's look at it right now, actually. Right, so this is, I don't know. I've never been to this website before, but Meta says it cuts CPU usage by 20% through kernel level profiling. So this low level stuff, I mean, you know, why not just write everything in Python and JavaScript? It's easy. Well, because at the end of the day, you know, places like Meta are companies, and if they can cut down CPU usage by 20%, that's a lot more money that they get to keep. So in the course of doing that, I mean, there's a bunch of stuff we're going to skip, but yeah, so tremendous server savings. Over 15,000 servers worth of annual capacity were saved in a single one-character code change, which was an ampersand. Right, so one of the problems that you may have run into, if you passed a vector by value. Oh yeah, I guess I can't write on this. Maybe I can. Right, so if I pass a vector in, say of a student, and if I pass that in as an argument, well, this is going to make a copy of everything in that vector, right? I'm passing it by value. If I just add a little ampersand here, well, now I'm passing by reference, and it doesn't make copies at all, right? It makes a copy of the memory address of the vector. But all the students inside I'm just looking at the original students. And if I don't want to modify them, I just make a const. Right? So these little things are big in terms of how much like CPU processing time you save, and also how much working memory you need, right? Because if I have to make a copy of all of this, well, this is going to go, well, it's probably going to go on the stack, which now means, well, I'm using more memory, but also like I have to watch I don't overflow the stack. So yeah, this particular one has to do with the auto keyword, which we haven't taken, but you know, if I want a shortcut to a type, I want to declare a variable v, well, I can declare it as auto and then put something here, maybe new student, and the compiler will figure out what I meant. The problem is if I want a reference, I have to say auto reference. So yeah, that was the particular problem with this. You know, just by somebody went through, but we don't need to be making copies here, right? So there was no ampersand. And so they put in an ampersand and saved a bunch of money. Anyway, I thought that was interesting and kind of relevant. So yeah, copies, standard template library. So the types of containers that are in this standard template library, well, there's sequence containers, which is what we've seen so far. That's what we've made so far. Associative containers, well, we did a map item, right? And a my map, that would be an associative container where we had a key value pair, and then a container adapter. We've actually also done that when we made the stack, right? So we made a stack out of a vector using private inheritance. That's similar to a container adapter where we want to sort of get rid of all of that extra public functions that can sort of ruin what we're trying to do. Iterators are a implementation of the iterator design pattern, right? They just, they're an abstraction layer between algorithms and containers. And algorithms are just global functions that perform operations on containers, typically using iterators. Right, so our little picture now, our diagram of the relationship is that my algorithms will operate on iterators, and the iterators will deal directly with the containers underneath. All right, so let's look at the first example, which is okay. So well, nothing we haven't seen before. We have a good old student class and a good old vector class. We're storing our students as student objects, right? So we're by value, I was going to say, which is sort of accurate. And then we're declaring when we're making a student, and also when we're making a copy of a student, and also when the student is being destroyed. So some of this will come as no surprise. We're going to push 4 students onto a vector, and then we're going to print out that vector. Okay. All right. So, well, there's a lot happening here. At the end of this, so we make a bunch of students. This is the initial students that we make, stack, push them onto the vector. We make a bunch of copies, more than we would think. Also, the destructor is called a bunch of times. I'm not sure if we looked at this yet, but I will quickly go over what's happening. This might be, I might be repeating myself a bit, but some concepts, it's not a bad idea to repeat. So my vector starts out, I have, it's pointing to nothing initially. And then I add a student and it says, well, I need room for one student. So it makes an array of size 1 and it copies student 1 onto it, right? Student 1 is over here on the stack and I copy it onto the heap. And then I try and add student 2 and the vector goes, well, I don't have enough room. So I'm going to make a new array of student objects. I'm going to copy student 1 over, and then I'm going to add student 2 to it. And then I'm going to delete the old one, which calls the destructor on student 1. All right, and then we're going to make student 3 over here on the stack. Well, again, I'm out of space, so I'm going to double in size again. So this time I'm going to go up to 4. I'm going to copy student 1, student 2 over, and then copy student 3 into the vector. And then I'm going to delete this, which we'll call the destructor on both of those. Right? So we see a lot of copy constructors being called and a lot of destructor calls. Not as many destructor calls, but you can see 1 here. We can see 2 here, etc. So that's what's happening. That is not very efficient. But sometimes we want to store actual student objects rather than student pointers. So, well, what do we know about linked lists? We know that, right, we know that they shouldn't make a copy, right? So the list from the standard template library is a doubly linked list, similar to what you guys wrote for your assignment 3. And once I add a student, it's in its own node, and then that node can stay in memory. I never have to delete it unless I remove the student, right? I never have to copy the student anywhere because it's just a bunch of pointers. I just rearrange the pointers. So technically, it would be more efficient to make a list of students, hypothetically, and add them to, well, make a list of students. So pushing the students onto the list. Okay, so here is where I push my students onto the vector. We can see all the copies and calls to the copy constructor, calls to the destructors. Here's where I push the students, the same students, onto my linked list. And indeed, I make one copy when I add the student, and that's it. Okay, so if I really need to store a student object, maybe a linked list is a better idea than a vector, which is going to incur, even though vectors are really fast, generally speaking, this is a lot of overhead, especially as the vector grows. All right, questions so far? Okay, well, our vector, we printed the students, so let's try and print that from our list. List. Well, so the linked list doesn't have this, right? So I think I briefly mentioned, but the subscript operator sort of indicates that we are using random access, which like an array, right? So I can just say like jump to this memory location and bring me back whatever you find there. But I can't do that with a linked list because I have to follow the pointers to get to some location in memory. So this doesn't work. All right, so how do I print out my linked list? Well, or how do I even access my elements? Well, we're gonna cheat a little bit. First, we're just gonna do student stu. We're gonna do a for each loop, which does work. And then cout stu and line. Okay, so this will work on a vector or a linked list, and so pushing the students onto the list and then printing them out. I should really mention that I printed them out, but this works fine. That is not quite as flexible as this random access, right? I can't access these things out of order. I have to really just walk through with my for each loop, but it does work. Incidentally, you can see here that I put a student pointer or a reference. This is the meta problem, right? Well, what if I just forget this reference? Well, it's going to work fine. When I go to print them, of course, I print the student, Matilda, and I can see here that, well, first I make a copy of Matilda, then I print Matilda, then I destroy Matilda, and then I make a copy of Joe, and then I print Joe, and then I destroy Joe, and then so on and so forth. So if I forget the reference here, then I am making a copy of the student every single time, right? So this is not just the danger of the standard template library, but the danger of C++ in general. Little things like this can affect your performance, right? It's still going to work just fine because I'm really just printing them out. And it's not going to matter in terms of what happens. It's not going to create an error condition, but it's going to be a lot less efficient. But yeah, so in this case, we like our linked list better, but we don't really have the tools to access it other than a for each loop. So let's see. Well, we can also use iterators. And yeah, so this is the example we just went over. We use a vector of objects. The objects are copied and destroyed as the vector grows. And although I didn't show that, if we insert or remove from the middle, I think I'll show it later. Well, objects have to be moved to make room. The same as when you guys were writing your little functions for the your collection classes. And we're going to make copies of objects when we do that as well. But when we put them in a linked list, we don't have those problems, right? I can insert in a linked list, no problem. I just have to rearrange some pointers. I have to walk to where I need to put it, rearrange some pointers, no copies are made, except for the thing being copied in. So yeah, we're going to look at another tool other than the for each loop to access things in our linked list. Not just the linked list, though, but anything from the standard template library. So we have well, this is our example from before, but no longer looking at a vector, just a list. So we're going to push all the elements onto the list, make sure it works, and then oh, I didn't print it. Well, all right, so we have a bunch of students. How do we print them? Well, we use a for each loop, but let's do something else. This list class and really all the containers have what's called an iterator, right? It is in the namespace of our list class. And I'm going to say this is IT. All right, and this iterator is like a pointer, right? It's not a pointer, but it behaves a lot like a pointer. You recall how we made a smart pointer and we overloaded those operators? Well, that's what they do with iterators. And so what I can do is say, well, it equals stulist.begin. Begin returns an iterator. It not equal to stulist.end. So we'll talk about these functions in a minute. And it plus plus. Right, so we're going to use a little bit of like, it appears to be pointer arithmetic. But it's really just an iterator that's overloaded this and figured, and well, every semester I think this would be great. I should integrate this into the assignment, and one of these semesters I will. But yeah, so how would you implement this on a linked list, right? Well, you would just go grab the next node, and that iterator would then contain the node, and I can return the student whenever I wanted. And how would I return it? Well, I'm going to dereference it the same as I would a pointer. And so yeah, now I have a thing that it's not a for each loop. It's like a pointer. It's not actually a pointer. It's just overloaded the same operators as a pointer. And yeah, so now we can print this out using this iterator. All right. Questions? Well, I'm sure you have some questions. So let's talk about what this begin and this end does. So iterator is just it's just a variable. But here we assign it the beginning and the end of our list, and those are actually iterators that our linked list makes. And so if I look at a linked list, and this, I'm drawing this as a singly linked list, but let's say it looks like this. So I ask for, and this is my stew list. I ask for stew list dot begin. Well, this is an iterator, and this iterator, and I'm going to give them some values here. So this iterator points to this first value. This points to A in this case, right? Or you could, probably it contains the node as well, although I'm not actually familiar with what they did for an implementation, but that would make sense to me. But regardless, this iterator has access to this value. So when I dereference it, I can say, well, here's the value you're looking for. So that's where my iterator starts. And then I have a second iterator, stewlist.end. So I said, keep incrementing that iterator it until, well, I say keep going as long as you're not equal to the end. Once you reach the end, we're going to end this for loop. And so what is end? Well, this actually points to just past the end. So if I dereference stewlist.end, I don't actually get a value back. If I dereference stewlist.begin, I get back the value A. But the reason why it does this is similar to a regular for loop, right? I would write something like for int I equals 0, I less than 5. I never actually takes on the value 5. Once it takes the value 5, I bump out of that for loop. And the same with this. So what does this give me? This gives me the element at location 0, the element at location 1, 2, 3, and 4. So if I have an array of size 4, then this is my for loop. And then once I hit 5, then this is data that I don't have access to, and I exit the for loop. So the same idea applies here. This stewlist.end points to just after the end of the list. Questions? Okay. Well, given that description, well, maybe I want to write these things in reverse. Yeah, let's try reverse. Oh, stop it. Okay, well, we have what's called a reverse iterator. I'm going to call that RIT. Oops, no. And then here, let's change these to RIT. You'll notice now that, oh, I can't use this. This assignment operator doesn't work anymore, right? Says specifically, no operator matches these operands. I have on one side, I have a reverse iterator, and on the other side, I have a regular iterator. So I cannot mix these up. So what I need is this, I need an RBegin function, which returns a reverse iterator, and an REnd function, which also returns a reverse iterator. And then basically, I can print my students from front to back, right? So from Matilda to Amy, and then I start again at Amy and down to Matilda in reverse. Okay. Now I can also do some fancy pointer arithmetic here, and instead of using reverse iterators, I can use my regular iterators and like decrement, right? But of course, this is I don't know, maybe a little nicer to work with. I somehow messed something up here. Oh, yes. Thank you. All right, excellent. Okay. The other thing is, well, let's say this is like a pointer to my data. So let's say in my student class, I have a set name function. So let's take advantage of that. And let's, well, if this is a pointer, I should be able to use the arrow operator and set everyone's name to Bob. And so then when I print it out, well, on the way down, I get Matilda, Joe, Stanley, Amy. When I'm printing it back in reverse, I get Bob, 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 Bob. All right, so like maybe I don't want to do that, right? So I can change this to a const iterator as well. And all that does is it says, well, the thing that you're pointing at, you can't, it's read-only, right? You can only call const functions on it. Set name is not a const function because it actually does make changes. So if I want to iterate over something and I want to make sure I'm not making any errors, accidentally modifying it, then I can use a const iterator instead. Const iterator and an iterator, it's just it's a qualifier, so I can have a const iterator that takes an iterator. Yeah. All right. Questions? Okay. All right, so yeah, our iterators, they have overloaded these operators, so I can treat them sort of like pointers. And in fact, I believe you can, so there's algorithms that operate on things like a vector, and I'm pretty sure you can just throw an array in there as well, right? Because if it's an array of pointers, then everything's just going to work. Again, because it's a template, all I need is if I replace t with some type, in this case, an actual pointer, as long as it compiles, it's going to work. So, yeah, so we have iterators now that we can use to access these members of the standard template library. Const iterators, the begin and the end. Again, begin points to something, end points to nothing, points to off the end. And if I actually looked at the reverse iterator, well, what you would think is the opposite, and you would be correct. So the begin, our begin, points to the last element, and our end points to just before the first element. Okay, so it just goes in reverse. Yeah, that's what I just talked about. There's also, we didn't look at it, but you can have a const reverse iterator as well. All right, so there are different categories of iterators. And what they have to do with is the type of container that's underneath them, right? We mentioned that, well, I don't have random access. I don't have a subscript operator in my linked lists. I do in my vector. And as it turns out, the iterator for my vector class also has a subscript operator, right? So there are sort of levels of capabilities of these iterators, although they share a lot of things in common. I do have these categories, and where the lower categories have all of the operators of the higher categories. So I have input, output iterators worked only for streams that we're going to see pretty soon. Forward iterators only work in the forward direction. Bidirectional iterators work forward and reverse. This is what the doubly linked list used, the bidirectional ones. We didn't actually walk, well, we walked in reverse using the reverse iterator. And then random access. So that would be our vector, things like this, the subscript operator, and pointer arithmetic. All right, so yeah, the category of iterator is determined by the type of container, as mentioned, vector. Of course, we have a lot more things we can do with a vector. A link, we sort of have to walk to where we get to. Import these operators so I can dereference it to get the underlying element, value, variable, whatever. I can use the increment operator, the assignment operator. I can assign it a value, right? It's going to, and equality, inequality for testing, right? So I can do my little for loops on any iterator. Forward, bidirectional, and random access also have these. Not so much the stream iterators, which we're going to see in a second. But of course, list and vector have begin and end. So I can ask for the iterator to the front of my list or the back of my list. And the increment operator, if it's a bidirectional container, then I have bidirectional iterators, which means I can do begin, end, and or R begin, R end, and the decrement operator. Random access supports the subscript, but also we get a lot of, we can use pointer arithmetic, right? I can add an integer to a pointer. I can skip, say, take this iterator +2, and it'll grab me the thing that's 2 away from it in the backing array or the vector or whatever it's using. All right, for optimal performance, what we did is a little bit the problem with this is that I should really store this and then use it, right? So I should say something like let's say end equals stu list dot end, and then right, I don't want to call the function every time. So for better performance, I would do something like this. And then I'm not calling stulist.end each time. But yeah, those are just little tips. Use the prefix increment and decrement. Again, I would have to double check, but I'm guessing your compiler would make a lot of optimizations on that. We're repeating ourselves here. So all standard template library containers provide a default constructor, copy constructor, destructor, and assignment operator. We didn't see these yet, but we'll take a look at them. But insert, delete, and clear, I can insert something into a vector. We've only been pushing things on the back. And same with our linked list, but I can do something a little more specialized. We have size-related functions, size, empty, max size, relational operators to compare 2 different types of containers. Comparisons are based on lexical-graphical order. If you're not familiar with that, it is add and advance. Well, if I think of this being a collection that contains characters, then how I'm going to compare these 2 collections is just to start by comparing the first 2 characters. And if they're the same, I'm going to continue. And then I'll compare the next 2 characters. And if they're the same, I'm going to continue. And then I compare these ones. D comes before V, so add comes before advance, and I'm done, right? And that generalizes to any type of thing we're storing in our container. So I can say is one container less than another, and it'll look and use the, as long as you've overloaded the operators, it'll do something similar to that. Which lecture does it start from? I mean, it's using aspects from assignment 3, right? So, I mean, it kind of dips into all of them. I mean, you have to make a collection class, but now it's going to be templated, but you still have to use all your proper like memory techniques and pointer techniques. So yeah. It ends at templates, I'll tell you that. I don't think there might be, I don't think there's any other concepts in there. But yeah, I mean, mainly focused on things since assignment 3, but everything makes an appearance. So yeah, to access our iterators, we have these. For my classes to be put in these containers, I should provide, well, we saw how many copies are made, so you should make sure that you're making copies the way you want, right? So the default might be fine. And if it is fine, then just leave it. But if you have any type of dynamic memory, if you say new in your constructor, then delete in your destructor, then you probably want to write these as well. You may want to sort or find things, so you may want to overload these operators, but we'll look at other ways to do that also. Okay, geez, oh, please. All right, so let's look at stream iterators. Down here, I guess. Okay, so we can do, I really like C out and C in. I think they're really elegant, the way that you can chain these things together. So what we're going to do is we're going to take that nice elegant interface and make it like really like ugly and awkward to work with. But it's going to illustrate input output stream iterators. Okay, so I'm going to say O stream iterator. Now, what is an output stream? It is, well, this is an instance of an output stream. And what does it take? Well, when I send something to the output stream, it looks at this type here and then calls the appropriate function for the type. So technically, when we make an iterator, we have to supply the type. We have to say what we're converting this into. So in this case, we're going to say strings, out, it, something like that. And then, well, we have to actually, which stream are we going to use? Well, let's just use the standard output. All right, so we have to give it a stream that we want to use to iterate over. And so we're going to iterate over this thing. And, well, oh, I guess I just clicked it or something. So we're going to iterate over the standard output. And what I'm going to do is say equals hello there. And let's do this. Okay. Look at that. Hello there goes to the standard output, right? So now I can take, that nice, elegant style from before, and now I do this sort of hacky C-like thing. But it works. I can't do, although I can send it strings, I can't do this anymore, right? This end line does not go through my iterator, or at least I don't know how to make it go through. There might be a way because it's C++, so there's always a way to do whatever you want. So let's say okay. So if I run this now, I get hello there, and then please input 2 strings. Okay, so let's input 2 strings. How are we going to do that? We're going to make a string. And take input from the keyboard. And then we're going to make a string word1 and word2. And then we'll say, well, so up here I said this equals a string. So down here, this sort of works in reverse, right? So let's say our string equals this. So W1 equals my iterator. Now it doesn't like that because technically these are iterators. So if I want, right, I say, give me the next string off this buffer, this input buffer. And it says, well, this is an iterator, my friend. I don't know what a string is. So I say, well, actually, just, if I dereference you, then I get back the value that's contained. So this will give me back the string. And then I'll say, your first word is, and then since I no longer have my elegant cout stream insertion operator, I have this hacky, append these strings together using the plus operator, but that should work. Please enter 2 strings, hi there. Your first word is hi. Excellent, okay. Let's grab word number 2. W2, Your second word is, all right. So hi there, and oh, my second word is hi. So what happened? Well, this is, I mean, I wrapped up my C in, and there's a input buffer, which is just a piece of memory that stores all the characters that I'm typing in. And then when I did this, I said, give me the first word, right, up to this first space or white space or new line. And so it did. It gave me hi. And then I said, well, give me the first word again, right? So I didn't advance. This doesn't actually clear anything off the buffer. So what I have to do is plus, I have to say, well, let's move past that word now and then give me the next word. So hi there, and my first word is hi, and my second word is there. So now it works. And that's a good question. And my only answer is an educated guess in that, of course, once I print it to the console, I mean, the buffer is cleared, right? I'm taking it from the buffer and putting it onto the console. Technically, if I wanted to, I could do something like this. It makes no difference whatsoever, right? So this will still actually just do the same thing. Hi there. Also, you'll notice that I didn't dereference this, whereas I could have, right? There are some liberties that you can take with the syntax here. Yeah, so in this case, it works fine either way. Except for the input stream. The input stream, it's picky. You have to dereference and you have to advance it if you want the next element. All right, question. Okay. Really ugly. I'm not even sure why you would ever want to do this, but there's probably a good reason. Enter words starting with N. Okay, so let's do this. So I have a string. I have a vector full of words. I have a vector full of words. Let's do a while, string equals in iter. And then I'll say while string is not equal to end. Well, what I'm going to do is then I have a word on here. So I'm going to say words dot pushback string, and then string equals in a iterator. But of course, I actually want to advance that first in iter. All right, so this should give me a vector full of words. Let's just make sure that it compiles before I get ahead of myself. Okay. It won't print anything other than hi there and hi there, enter, how are you, enter, end. So it keeps going until it encounters this end. All right, now let's print it out using the algorithms library instead of a for each loop or something like that. So I'm going to make make an output stream iterator string. And then, well, I'm going to do this. I'm going to say copy. What's it called? Words dot begin. From the beginning of words to the end of words. Put all of that on the output stream iterator. Right, so this is a function from the algorithms library. It takes 3 iterators, or at least 3 iterators as arguments. There might be a version that takes a different number. There might be other versions of this, but this is the one I'm familiar with. So I go from words.begin to words.end onto this iterator starting at this location and then advancing, it's going to call plus plus on this each time, which will do nothing, but should make everything come out onto the screen. So hi there, how are you? And it outputs hi there, how are you? The spacing is not the greatest, but so yeah, well, this actually takes a second optional argument. So a delimiter. So when I am sending things, every time I send something to this output stream, I then send one of these tokens. So hi there, how are you? And then they have spaces. And I could do, of course, if I wanted to, something a little different. And yeah, so now they have stars in between them. All right. Delimiter. Yeah, so that's everything there. So yeah, now that I've wrapped these input and output streams in iterators, I can use the algorithms library on them, right? Which maybe the other stuff is pretty ugly, I think, but this might come in handy, right? That's a short way to send everything to some stream. Questions? All right. So yeah, when we make an output stream iterator, we have to tell it which stream we are making an iterator on. In this case, cout. This could also be a file stream. And then we can write something like this. Here I did dereference it. Of course, we saw that we don't have to. And then yeah, now that it is wrapped in an iterator, I can use algorithms on it. So just these global functions that take iterators and do things to them. All right, so that is the streams. We also have sequence containers. Vector, list, and dec are the main ones. Useful member functions, front, so give me the front thing, back, give me the back thing, push back or pop back. We've seen some of these before. Yeah, vector is like Java's array list. And it's a good, if you're wondering what's the best data structure to use when you make something in C++, it's vector. It's almost always vector, right? You have to have a very good reason to want to do something else. And so when we get to, actually we may not get to performance this semester, but you can see why as vector stores everything together in memory, which is actually kind of important for like making things cache friendly, whereas doubly linked lists don't. But of course, if I am storing objects, doubly linked lists don't make copies, so that might offset it depending. Well, we can always store pointers. Insertion and deletion. As promised, here is the vector. We're going to look at some of the things. Well, we already saw how we can copy a vector to a stream. We can also copy a stream to a vector. But to start with, we'll do the exact same thing. Just enter a bunch of words, copy them out, and then well, an output stream iterator is just an iterator, and this copy, it doesn't matter what type of iterator. I can copy to any type of iterator. And in particular, I can copy, in this case, to another iterator from a second vector, right? So if I want to copy everything from vector number 1, from begin to end, onto vector number 2, start at the beginning, I can do that. Although I'm not going to do that today. There are a couple things we have to keep in mind, of course, because it's C++. There's a bunch of low-level details we have to contend with, but we'll look at that next class. We'll finish off the standard template library and perhaps start Yeah, so standard template library is what you need for tutorial 10. Again, I'm going to open up the tutorials next week, so be ready. If you're not happy with your mark, now's your opportunity to make some of those marks back. And otherwise, yeah, assignment 4 and tutorial 9, and I'll see you guys on Wednesday.